Okay, hi everyone. Can you hear me?
Yes.
Okay, great. Okay, so I prepared some slides and shared them in Spectrum, so you can get these slides later, yeah. And also there is a set of notes about ensemble methods, right? Which we are going to talk about after the break. Right? So you can also look at that. There are some more technical details in those notes. Okay, so today I am going to cover some remaining topics, right, with supervised learning, all right, on a particular model-free supervised learning method called K nearest neighbor. And after that, I'll say something about unsupervised learning. And then after that, we will look at ensemble methods. So that would more or less complete an overview of commonly used machine learning methods, right, and data mining methods in the field. Of course, there are a lot of new innovations. We generally those that are very recent ones we don't. You may come across in some kind of computing packages and all that, but for theory, we cover the things that are a bit more well established, right? Okay, so to start off, so this K nearest neighbor method is actually belongs to a class of method called distance-based methods. So this method is basically it's very simple. You basically decide whether a test sample belongs to a particular class depending on the nearest sample, depending on the sample that's nearest to it, right? So if the nearest sample to, for example, your test sample is a plus, then you will you might actually just classify it as a plus, right? And of course, that's why this is called nearest neighbor, yeah. So of course you can use the rule of either one neighbor, 3 neighbors, 5 neighbors, and so on, right? And in general, any odd number of neighbors. We generally do not use even number of neighbors because we want to avoid ties, right? If you use even numbers, then, for example, there are 2 neighbors that are plus, then another 2 neighbors are minus. So then it's tight, right? So it's hard to make a decision, right? So usually the K is set to an odd number. But then the way you actually compute the distance actually matters, right? Using different, there are many different notions of distance. Okay, so we're going to look at these notions. Okay, so so if you have any data vector, right, you can associate it with any class label, right? Say +1. If its overall similarity to vectors belonging to +1 is higher than similarity to vectors belonging to -1. Okay. And then you can basically use a distance metric to quantify similarity, right? So highly similar samples will have a small distance between them, right? But then you first need to determine what distance actually means. Okay, so this is a general, this is actually a generalized distance called Minkowski's distance, right? So the distance between 2 points, yeah. So you basically have these are 2 vectors, right? So this is one vector x, vector y. So the distance between them is computed as follows. So you take the absolute difference between these 2 vectors, well, and then you raise it to the power of 1 over p. And so this is kind of like what we call a Minkowski distance of order p. And usually sometimes it's denoted in the, this is a form that's called a norm. Right? Okay, so basically, for example, you might have a, if you have a data, right? So these are your features, feature 1, feature 2, feature 3, and so on, feature P. So this value can be 5, -1, 0, and so on, right? So let's say this is X, and this is Y, right? So these are your samples. So let's say this is 5, this is -1, this is 0. Let's say this is 1. So if everything is exactly the same, then you basically here you are doing term by term, right? Actually, this I should put P. Well, actually, I use a different notation here. Here maybe, okay, here is actually D. So I use the P for the order here. Okay, never mind, it's just a notation. So basically we look at it term by term. It's very easy. You look at it term by term, all right, and take the difference. And then here you take the absolute and raise to the power of 1 over P, all right? So, okay, so then, so it's very easy to do. And so we look at some special cases, yeah, like if your P is equal to 1, okay, if your P is equal to 1, then in this case, P equals to 1, let me annotate. Okay, so P equals to 1, so this is 1, so basically this is sum of the absolutes. Okay, so this is called a Manhattan distance, right? So Manhattan distance is something like this. So let's say you have a grid. Manhattan distance is actually a movement along a grid, right? So for example, you have point A to point B, right? Let's say these are 1 units, right? 1 unit, 1 unit. So the Manhattan distance from A to B is basically 1 unit, 1 unit. So it's basically equals to 2. Okay, you can also go from here. All right. This is actually modeled after the city of Manhattan, right? Manhattan is in New York. Okay, so the city planning there is in blocks of buildings. So in order to get from one building to another, you have to go by grids. You, like for example, point A, point B, you can't actually cross that diagonally. Okay, but you have to go by grids, right? So the distance is computed as you have to follow the path, right? So if you have 2, then it's a normal, your usual Euclidean distance, right? If you have 2, then basically it will be the sum of xi minus yi square root, okay? So basically this is your Euclidean distance, okay? Which everyone is familiar. So our normal usual mathematical space is a Euclidean space, right? And then so then the other ones are a bit weird. So we generally don't use those like P equals to 3, 4, 5, and all that. They actually go to some actually abstract space. So we generally don't use them, right? We basically use 1 and 2. Of course, there are also special cases. If you take limit, yeah. If you take limit, go to 0, right? So this is what we call a Hamming distance. A Hamming distance basically is just counting the number of differences. Okay, and then when your P goes to infinity is something called Chebyshev distance. So these two are generally not used in generic machine learning. Hamming distance is usually used, it's actually a kind of simplistic method used to compare two sequences, right? Sequences of words. For example, if you have, let's say, apple, right? And let's say an ankle. So the Hamming distance between these two words will be 2, because there are two positions where the characters are different. So their Hamming distance will be 2. Right? It's just something very simple like that. Okay. So we'll focus more on one Manhattan distance and Euclidean distance. Okay. Right, okay, so distance measures, they usually will satisfy a few properties. So first thing is that they have to be non-negative, okay? Minimum is 0, right? Which means there's no difference between 2 points. The distance is 0. Then identity, okay? If the distance between two vectors x and y is equal to 0, then it basically means that there can only be one possibility, which is both vectors are actually the same thing, right? And then symmetry. So the distance from point A to point B is the same as the distance from point B to point A, right? So where you start doesn't matter. And then you have triangle inequality, which is basically if you have, this is a common triangle inequality. So you have x, y, z, right? So the distance from x to z must be, okay? So the distance from, you go from x to z, right? It must be less than or equals to, if you have an intermediate point here, so it cannot be longer than if you go from here, okay? All right. So this is the so-called triangle inequality. Now, these distances are very easy to use, but they actually have a problem. Because if you look at the way it was defined, okay? These are actually what we call mathematical distances. It's actually figured out by mathematicians, right? Who do not have, who are not applying any statistical ideas into distances. So basically, when you sum this, right, it means that each of your variable is actually given the same weightage, right? You're saying that, for example, because over here, when you calculate the distance, right? So this is your feature 1, feature 2, and so on, right? Let's say this is 5, this is 4, this is 3, this is 0, and so on, right? So at each of the features, you will take the difference. Let's say if you use the Manhattan, is basically for this part, for the first feature, you take absolute of 5 minus 4. For the second feature, you take absolute of 3 minus 0, and so on, right? And then you basically, then you sum all of them together, all right? But when you do this, basically you notice that you are basically giving a weight of equals to 1 to each of the features, right? So each feature receives an equal weight. And this may not actually be a good thing, because in practice, your features, right, are correlated, okay? So if you do not actually do some transformation to your features, like for example, if you do principal component transformation, then your principal components are all uncorrelated, right? And then if you calculate distances, then they will behave properly, right? Distances, if you use all the principal components as a data vector, then the distances will be very well properly calculated. But if you don't do principal component and you basically just have some features and then you calculate the distance, then this distance basically is having a lot of redundancy, right? Because if your variables are highly correlated, then depending on how many are correlated, then you basically actually have less number of variables than you think you have. Okay, if you have 5 variables, 4 of them are strongly correlated, then basically the effective number of features you have is probably somewhere around 2, right, rather than 5. So this is one aspect that needs to be considered when you use distance methods, right? And for the statisticians, they basically prefer to use the Mahalanobis distance, right? The Mahalanobis distance basically is given as follows. So it's very similar to the squared. This is more like the square. It's very close to the squared Euclidean. Okay. The squared Euclidean. Except for this part here. So this is your covariance matrix. Inverse. Okay. So basically, it takes into account the covariance between your variables, right? And it does some kind of matrix multiplication here, right? So if you remove, so if your S is the identity matrix, then basically your distance between x, y will be basically just this, okay? And this is basically the sum of xi minus yi squared, okay? Okay. Okay, so so now let's look at the k nearest neighbor. So k nearest neighbor is actually very easy to do. In fact, this is k usually is denoted as KNN. Okay, KNN. It's very simple. So for example, let's say you have is basically model free. Yeah, you do not need any particular model at all. Basically, you just need to define a distance function. Define a suitable distance function. And then after that, the way to do it is like this. So if you have a data point like this, let's say it's distributed in such a way. Okay. So this is your training set, yeah? Suppose now you have a test set. So let's say you put, if your test set is sitting in this space, yeah? So if you use k equals to 1, that means it will find its nearest neighbor. And then, so in this case, the nearest neighbor is this guy. Right? So then it sees that, oh, okay, it's a plus. So you will label this sample with plus, right? So if let's say it is somewhere around here, the closest is to negative. So it will label it as negative, okay? And of course, you can use k equals to 3. If k equals to 3, that means like in this case, it will look at this guy, the 3 nearest. So the 3 nearest will be this one, and this one, okay? So after that, you take majority vote. All right. So if the majority says that it is a plus, then you will go with the plus, right? So of course you can extend it to case of 5 and all that. So if you extend to case of 5, maybe it will go until, so the nearest 5 will be 1, maybe this one, and then maybe this one, right? So there will be 4 plus and 1 minus. So the majority is still plus, so you will label it as plus. Okay? So it's very simple. And because of its simplicity, it is also, because it's very flexible, right? It's completely data driven. So it can actually handle very not highly non-linear feature space quite well. If in fact, you might want to consider this model as some kind of what we call so a lot of machine learning experts, yeah, they know how to make sophisticated models, right? If you are, but it doesn't mean that sophisticated models will always win, although they tend to, but not always. If you're just a beginner or junior data scientist, right, you don't know too much about more sophisticated models, you can always deploy KNN, and it usually will give some decent results, right? So this is one of the things that you should consider. Of course, you basically in terms of explanation, there's actually no explanation. Yeah. If KNN is good for predicting, not good for explaining. Okay, because it is a completely model-free method. So if all you want is prediction, all right, you give me a data, I can tell you what sort of in regression problems you want to give it some value prediction, or classification problem, you give it a label. If this is only what you care about and you don't care about explainability of the model, then KNN is a reasonable approach, right? But otherwise, if you care about why the classifier behaves in a certain way, then KNN is not a candidate, right? Because it basically is just a model-free approach. Okay. Okay, so here are some examples of how the choice of the the distance function affects the decision boundary. So in the first example here, if you use Euclidean distance, all right? We use Euclidean distance, then your decision boundaries would look like this, okay? So anything, for example, anything that is, so this is a decision boundary. Okay, the decision boundaries are here. Let me just draw them. Okay, it's going, there's one here. Let me see. Okay, there's one here. So if you, meaning to say that if you have a point here, right? So it's basically closer to this. This is like some kind of reference, right? So the distance, so all the points that are here, right? They are basically closer to this this point than to the other points. Okay, suppose you basically, if you, let's say you use these 3 data points, and you use let's say k equals to 1 case, right? So if you put a sample here, the nearest neighbor will be here, right? So basically you see that this region is all red because anything that is actually around here, the Euclidean distance will be closest to this point, all right? So this is a k equals to 1 example, okay? So so over here, so it's basically on, if it is falling on this line, then it's actually a tie, right? Because so here, because the distance to this point and this point is actually the same, all right? Okay, so if you kind of like look at it a bit more carefully, right? So you can more or less see that over these points, they kind of like can go to this part and this part equally likely. Basically, it's like a circle, right? So any points here is basically you have a radius going like this, and then it's circle. So the distance is the same. Okay. So that's why at the end you see that if you have a point in the middle, all right, its distance to this, this, and this is the same because they are lying on the circle here. Okay. Now, if you use the Manhattan distance, your decision boundary will change. Okay. It will change because in any point, right? Like for example, for a point here, okay, you want to, so the point you calculate the distance is going like this. It's looking at the distance from here to here, right? So this one is, okay, the distance is like this. So this one, the distance is like this. Okay, so of course, any value that's here, it will be grouped as red. So let's look at, for example, if you have a value here, right? So basically, here, so the distance to this point is going like this. The distance to this point is going like this. And this length is the same, yeah? So let's say, for example, you have another one which is here. So basically, you go like this, and this one you go like this, okay? So the distance is the same, yeah? Okay, you can approximately see that. So this one is going like this, and this one is going like this, and the length is the same, right? So for this one, it's sitting in the middle, so it will go like this, go like this, and go like this. And these three lengths are the same, yeah? So if you keep on plotting a lot of these, then basically you can infer the decision boundaries will look geometrically it will look like this. Okay, so your decision boundary actually is affected by the choice of your distance function. Okay, and basically your distance method, and if you use the Euclidean distance, the decision boundaries that are induced, basically they form a kind of mathematical structure called Voronoi tessellation. Basically, so Voronoi tessellations will form the decision boundaries, yeah, for your Euclid, for your k nearest neighbor classification, right? Okay, with k equals to 1. So it will form like this. Okay, so you can see that they kind of like form polygonal decision boundaries. This is just to give you some basic ideas. Okay, we're not going too much into this. Okay, so basically that part is quite short decision. K nearest neighbor. So maybe I just develop a bit of intuition about k nearest neighbors. Now, what happens when you have k equals to 1 and the case when k is like high, say 21. So how does the difference in the choice of k affect the behavior of your classifier. So here, if you have k equals to 1, your KNN classifier will have the following features. The bias will be low, but the variance will be high. On the other hand, if you set your k to be high, the opposite will occur. The bias will increase, but the variance will drop. Okay, so what does that mean? So generally you might have to choose some reasonable k. Okay, which is not obvious. It may vary from data set to data set, but generally something that is maybe sitting in between 1 and some high value. You may actually need to use different values of k and then compare your KNN classifier with different values of k to see which one is more reasonable. So you basically want to get some kind of a balance between your bias and your variance. Now, how do we understand this? Now so now if you have k equals to 1, right? So basically what happens is that if you have a test sample, right, it just needs to look at the nearest person, nearest sample, and then it will take the label of the nearest person, nearest sample, right? So the bias is low because if you repeat this procedure many times, right? Let's say if you keep on repeating this procedure, all right? Say maybe your S is here, maybe your S is here, and all over the space. And if you use a k equals to 1, then on average, okay, if your plus and minus class ratio is more or less balanced, then on average, half of the time it will be a plus and half of the time it will be minus, right? So it doesn't go to any particular class, okay? In that case, we will say that the bias is low, right? Because on average, whether it takes a plus or a minus, it's kind of like balanced, right? There's no particular bias. But the variance is high, right? Because every time, right, it can change very easily depending on whether it is close to a plus or close to a minus, okay? So the variability is very high if you use this method. Okay, this is something like an example, an analogy of this will be, let's say you want to form an opinion, all right, about certain things. The way you do it is you just ask one person, you ask the person's opinion, and then you just follow that person's opinion, all right? So that would be analogous to the k equals to 1 situation. And if you imagine yourself doing this many times, right? You repeat this procedure, then sometimes you meet someone who has opinion A, you just go with opinion A, all right? And then you meet someone with opinion B, then you just go with opinion B. So on average, you basically will, if opinion A and B are more or less equal, then basically there's no, basically your bias is more or less cancelled off, right? But then your variability is very high because you don't know what the next opinion is going to be, right? Because you only, it can switch from AB, and just without any particular direction, right? So the variability will be high, okay? Now, if your K is large, then your bias will increase, but the variance will drop. Now, how do you see that? Okay, so let's say if you actually have more plus here, right? So basically, if you require a lot of the neighbors, then the majority class will have an advantage. Because There are just simply more of them around, right? So if you ask for more neighbors, right, the neighbors will tend to be belonging to the majority class, right? So then naturally your let's say you have a sample, your nearest are all here. But this is maybe if you just, it is simply because you have more plus in the sample, okay? So your bias will be very high because every time it will just go to the majority class, all right? Simply because the minority class, they are too few. So in this case, your model will have a biased performance. It will always try to predict to go with the majority class. So then you'll know that, let's say if you do fraud detection, right, using KNN, you better not set your K to be high because your model will be useless, yeah, because in fraud detection, most of your samples are normal samples, right? You don't have fraud. Your fraud usually is like less than 1%, something like that. So if you use a K that is large, right, your model can never detect the fraud cases because it will always go by the majority, okay? So with this kind of understanding, you can perhaps tune the K parameter depending on your situation more accurately. Okay. So, but the variance will be low because every time your prediction will be going towards, your prediction will be stable, right? It will go towards the majority class. So if you do this like 100 times, right? Maybe 99 times is going to plus. So there's not much variability in your prediction. Okay. So in that sense, we say that the variance is low, right? But that may not be a good thing, okay, because your bias is high. Right, so these two situations are not desirable, yeah. Okay, low bias but high variability means your model is unstable, and it can basically be influenced very easily, yeah, by minor small random perturbations. The other one is there's actually if it's biased already, then even though your variability is small, is misleading you. So that's why you have to find some compromise, yeah, okay? Find some compromise where you have your bias is not too high, and then your variance is also not too high, right? So this is something called is the bias variance trade-off. Okay. In fact, there are no perfect methods, yeah, where you have that will decrease your bias and decrease your variance. The only situation where both of these things can go down together is when you have increased samples. Okay, increased representative samples, right? If you study some mathematical statistics, then you will in mathematical statistics you also have this concept of bias variance trade-off, where when you try to develop estimators of some parameters, right? So certain estimators are biased, but their variance may be low. But some estimators may have a high bias. Okay, the bias may be there, but then the variance is lower. Okay, so basically you have to decide some trade-off, right? You need to decide which estimator may be more reasonable. So it's the same here. It's similar kind of concept in machine learning. Yeah, there's a bias and variance also in the behavior of the models. Okay, so in mathematical statistics, what you have is that suppose you have a parameter, your parameter is, let's say your model parameter is 0, right? So you may have one estimator that is unbiased, right? The distribution of, let's say, theta hat 1. This estimator may be like this, and then the other estimator may be like this. Okay, so the first estimator, right? So this one actually has a bias. It has a, let's say this is minus 0.5. Right? So you look at estimator 1, okay? The distribution is like this. Estimator 2, the distribution is like that, right? So although estimator 1, right, is actually unbiased, right? So it's centered on the true parameter, right? But you see that if you do it different times, right, you may actually get the spread like this, okay? For the red one, is biased because on average, it actually will not, its average will not be the same as the true parameter value. But then, you know, its variance is actually small. So it will just run around here, all right, more or less. Whereas the other one will run across a wide range, right? So in this case, you might actually prefer a biased estimator rather than an unbiased estimator, right? So because of, based on the trade-off, right? Yes, you do have some bias, but overall, this estimator is doing better. So in the mathematical statistics situation, you use the root mean square error, right? It's called the root mean square error. Okay, which basically is equal to the square root of the square of the bias plus the variance. Right. So over here, you also have a similar situation like this, but here we are just, here we don't have a formal way to work out, okay, this calculation, except when you impose some kind of models. So, but then this is to give you some idea, right? That when you construct your classifier, you may want to think about the issue of how to set the parameters so that your bias is not too high and your variance is also not too high. Okay. All right. Okay. So I'm basically done with K nearest neighbor. All right. And now I want to say something about unsupervised clustering. So so unsupervised clustering as or unsupervised learning. So in this case, basically you want to, so there's no label, right? So unlike supervised learning where we actually have label information, you nowadays you can frequently come across data sets where there are no labels. And these data sets are also very important, okay? I'll give you some examples of these data sets with no labels. Now, if you, the very common ones are in e-commerce. Okay, if you have e-commerce, you get customer data, right? Then you want to basically profile your customers, okay? So you want to say, okay, so you have a database of customers, right? Let's say if you work for Lazada, you work for Shopee, whatever, right? So you get all these customers who buy things from you, and of course you can record them, right? Record their information. Some you can mine some information from them, like their purchase history, what did they purchase, and so based on that, right, you want to kind of like profile them, all right, so that you can target certain advertisements at them, right? So if you look at if you have bought something before at Amazon, and then you know that they have a very effective way to do this. Okay, every time you go there, right, if you have bought certain things before then, when you go there, it will kind of like pop up certain advertisements, will pop up with certain recommendations to you, right? So that's because they've already profiled you based on the behavior of other similar kinds of behavior, right? And that is totally cannot come with a label because no one is there to label it. Okay, it's not like, let's say, all the data sets that you work with, right? For the continuous assignment, those data sets, you have the label information because there's actually some independent information that's been used to put the label to samples, right? Usually that costs money, right? If you ask someone to, usually the labels are given by a domain expert, okay? Or like, for example, if you have a lot of images, right? You want to do machine learning of, let's say 1,000 images, which may be, you want to label them as being whether animals or plants, right? These two types, for example, or inanimate objects. Then, well, if you want to label them, then you either label it yourself, right? Or if you have 10,000 images, you got to do them one by one, you know. Okay, you got to look at them one by one and label. Of course, the advantage is that if you label them using a human being, right, then if the picture is not too complex, then usually you will get very high quality label information, right? But then you have to pay this person, right? Okay, and then if the payment is maybe not such a big issue, but the biggest issue may be scalability. So when you need to label the samples, right, it takes a long time to do that because a human being can only work for a certain number of hours. Okay, so yeah, if you need some kind of immediate kind of algorithms that work on real time, right, then you cannot use human beings to label the data, and you have to discover the labels through a data-driven method. Okay, so unsupervised clustering is actually has a lot of useful applications, right? Especially for large volumes of data. Okay, so, but here we will just look at one very simple example of the unsupervised learning, which is called the K-means, right? K-means clustering. So K-means clustering, right? Okay, so basically the algorithm is like this. It's very simple. The algorithm is very simple. It just consists of iterations of 3 steps, right? First is that suppose you have this is your data, right? So this is your data, okay? So you have to decide, you have to tell the algorithm how many clusters you believe there are. The minimum is 2, and then you can go on with 3, 4, 5, and so on, okay? So if you start with, in this example, it starts with 3. If you say you start with 3, okay, what happens is that, okay, so suppose this is your feature space, right? We'll just use a 2-dimensional feature space to make it easy to explain things. So it will then randomly find 3 starting points, right? You will find 3 random starting points. And then after these 3 random points have been, so the 3 random points can have their own labels. You can maybe take a label of red, green, and blue in this case, right? So after that, you will find the distance, yeah, of each of these points, right? You will find the distance to, okay? So basically you'll find the distance of, so you have basically a distance of x to, let's say, the red. And then you'll find the distance of x to blue. And then you'll find the distance of x to green, all right? So you have these 3 distances. Of course, you can use Euclidean distance, right? Here, of course, the idea of the distance is so important. If you use a different distance function, you will get different results, okay? So if you work with Euclidean distance, then you have these 3, and then it will take the following: the argument that minimizes this. So the argument that will minimize this 3 things, right? So this basically just means that, okay, what is the minimum, right? You got these 3 distances. It will find, let's say if this is this one, right? So the argument of this dx blue is blue lah. Okay, this is the argument, right? So then it will assign blue to that. In this case, it's red lah. Okay, in this case is red because red is closest to red. Yeah. So basically all these points, right? You find the distance, you calculate, and then you use the argument, right? So you repeat for this and so on, right? Basically the same thing repeated for multiple times, okay? And after one round, right, you will find that this is a situation, right? So these are all more similar to green, this green, okay? So okay, so after you have got this thing done, so you can see that this is some kind of, this is just to show the partition, right? After that, you basically you will remove this point, this initial starting point, and then you will update, yeah. So you will update the this centroid, right? You will remove and then you replace it with an update. Okay, you update it with the green ones. This one you update it with the red one, and this one upgrade with the blue one. So you can see that since here there's only one point, right? After you update, it will just move here. Okay, you see here? So your initial point will just move here, right? After updating, and this will basically you take the center of this point, so you'll basically the new one will be somewhere around here. So move here. So this one will maybe move somewhere around here, right? So after updating, you will get this, right? And then basically then you repeat, right? After you update, you repeat. So after you update, right, then the next time you do, these two values will be closer to red. So then you will get this result, right? And then you keep on updating until you basically you keep updating, okay, until the position change of your centroids, right, is below some threshold. Okay. So once the changes are very small already, then you stop the algorithm. Okay, and then it would have converged. All right. And then after convergence, right, you can compute some ANOVA-like quantity. You compute the between cluster, the sum square between cluster, and you divide it with the sum square within cluster. Okay, so this will give you some idea about the compactness of your cluster. If the clusters are very compact, then the sum square between cluster will be large. Okay, if you have if the clusters are very compact like this, let's say like this, so the variation, the sum square between the clusters, right? So the sum square between the clusters will be high. Sum square within clusters are the variation within the cluster will be low. Okay, so in that case, your in this case, your sum square between, again, sum square within will be high. All right. So next slide. Okay, so basically, the previous procedure, we will try for k equals to 2, k equals to 3, k equals to 4 until some, you need to decide, let's say up to what value you try, right? So after that, you can plot what we call a SQB plot. Okay, so this is your k, this is 2, 3, 4, 5, and so on. Okay. So first thing is your sum square between to sum square within, right? So if let's say the real number of cluster is 3, you will get something like this. It will shoot up, okay? And then after that, further increments will be very minor, okay? So it will like, go like this. So you basically determine that the number of optimal cluster is 3 based on the largest jump, right? The largest jump and then followed by very small jumps. This is because if you have a cluster like, if you have 3 clusters, right? Let's say suppose this is a very clear example of you're having 3 clusters, right? So the algorithm, of course, will converge to 3, and then if you have 3 here, then so this is one cluster, one cluster, one cluster. So it's sum square between to sum square within will actually be higher than, let's say, if you do 2. If you do 2, maybe perhaps it will group this together, and then here, all right? So here your sum square within will actually be larger, so it will be in this situation. And if you make 4 groups, then basically you are having unnecessary clusters. Let's say you maybe split another cluster here. You are saying that, oh, I have one here, and one here, right? But then over here, the increment, since you capture most of the sum square between variation, so this is still high. And here you basically, because you are creating a cluster here, so usually the sum square between will drop, right? So then you have a minor increment, okay? So but then you may find that this cluster may not be meaningful, yeah, because it's too close to this one, right? You might as well just work with this cluster, okay? So basically the way to check the optimal K is to do the scree plot, all right? This is one way to do it. And the other way is there's a graphical way called the Kaufman, Rosso, Silhouette plots. Okay, so let me show you this one. So it looks something like this. Okay, so this is an example. Okay, so here if you do, so here you naturally see that there are actually 4 clusters, right? So you look at this Silhouette plot, okay? So basically you will see that it has something that looks like a blade here, right? Looks like a knife, right? That's coming from the left, okay? And this one, if you specify your K to be, you over specify, let's say you say that there are 5 clusters. So then it breaks an additional, it splits out this cluster into 2 halves, right? So then you can see the corresponding colors here, okay? But then you see that over here, the Silhouette coefficient, right? Some of them are falling below the average. So this line is the average. You basically average out these things. The way to read the Silhouette plot is that if all the Silhouette coefficients are above the average here, then this K is the optimal K. If in this case you find that 2 of them are actually lower than it, right? So in this case, it indicates that you have kind of like over specified the number of Ks. Okay, so this is generally the way to read Silhouette plots. The Silhouette plots and the scree plot are 2 what we call informal ways to determine K. Right. In some cases, when the K is very obvious, then this method will work. Right. But in general, right, you may want something that's more formal, right? Because sometimes it's very subjective, right? It can be subjective for different people looking at a graphical diagnostic plot, whether they agree that certain things, they agree the same thing, except in very clear-cut cases, right? Like for example, if you look at QQ plots for checking normality, depending on different people, right? Unless the case is very clear, then otherwise sometimes some people based on a QQ plot may think that the data is normally distributed. Some people may not. Okay, so if you want something more formal, then there is actually work, right, done by Tipshirani. Tipshirani is also the person who co-authored the work of bootstrapping with Efron. Okay, so this is a very useful R package called cluster, and this basically this R package uses some technical results called the gap statistic, right? And it basically gives you a more formal framework to estimate K. Okay, so I am not going to go through all these things. These are very technical things. So basically, it computes some kind of quantity called the gap statistic. So, okay, so basically you can see that the steps are here. First, you start with the number of clusters 1, 2, 3 until big K, right? And then you have within dispersion measure, right? So this DII is some kind of a distance function, right? So basically it's like this. So basically, let's say you have your data like this. Okay, so let's say if you start with K equals, so of course this is basically unlabeled, so I should put the same thing. So if you start with K equals to 2, right? If you start, let's say you have one cluster here, one cluster here, your within dispersion will be, let's say you take the centroid and then you'll find the distances, right? Just find the distances from the centroid. Okay, so this will be the dispersion measure. Okay, so a cluster that is compact, right, will have a smaller dispersion compared to a cluster that is non-compact. And then basically after that, there's some kind of technical work that involves the gap statistics is computed as using some kind of statistics like this. Okay, so this one is that you don't actually need to really go into this one. This is just to give you some idea about their algorithm. So anyway, if you apply the package, basically it will just tell you which is your optimal K, right? And you I think it will return some p-values to you, right? To do some kind of statistical tests on which of the K's are statistically the correct number of clusters that you should use. Okay, so this one, if you are doing unsupervised learning and you want to find the number of clusters, then this is a good package to use. Okay, so I show some results. These are some output from the program. So let's see. So this case is the case of so this is the distribution. So this is an example. So basically I have data in this space. If I start, of course, K equals to 1 means there's actually no cluster, right? So everything, you take everything as 1. Okay, then you see that if you take everything as 1, right? You take everything as 1. Then within sum of squares, WK, right? So basically you have a centroid here, so then you can calculate the distance, right? Okay, of course it's going to be very large, all right? Okay, because there's small variability if they are assumed to be from the same cluster. But then the moment you have two clustering, so it will converge to here and here maybe. So your sum squares, right, will start to drop, okay, compared to the previous one. And then if you do three clusters, so maybe there will be one here, and one here. So then it will drop further, right? Because the sum of squares to the centroid in this cluster will be smaller, right? That's why it drops, right? You can have, let's say 4, maybe 4, it will be something like this, okay? So then that's why the point is if you keep on increasing K, it will definitely drop. But we are not interested in defining the number of clusters, right? So we just want to find an optimal one. So basically it will produce some diagnostics like this, right? So this is observed expected, and basically we look at this plot here. So the number of clusters, you will see that this is the gap statistic. The way to look at it is like this. You see that there's an error bar here, okay? So it actually does some kind of more sophisticated way to tell you the amount of variability in this gap statistic for a particular K parameter, right? So you can see that your estimated gap statistic is here for K equals to 2, right? Here is 2, right? Okay. Now notice that these are I think this may be the confidence interval. Not sure, but it's an error kind of error band. So you can see that K equals to 2, right? So the error band around it is over here. For the rest of them, right, you see that their error bands are not overlapping with those of K equals to 2, right? So it tells you that your gap statistic, right, for K equals to 2 is significantly different. Significantly different from K equals to 3, 4, 5, and so on. Right? So, and you will take the one that is the highest gap statistic. So in this case, very clearly, you will consider K equals to 2 as the optimal, the most reasonable number of clusters. Okay, so for those who are working on projects related to unsupervised learning, okay, so this can be a useful useful package to look at. It's actually quite easy to use. This package is quite easy to use, so you may want to try that. Yeah. Okay, so here's another example. Okay, so in this example, what do you see here? So basically, this is more or less like random, right? Okay, they're randomly scattered. There doesn't seem to be any reason to make any clustering. So as a result, when you look at this, the distribution, let's say you look at the within sum of squares, the decay is actually not, so over here you see that the decay is very sharp towards the optimal K, and then after that it's very flat. But this one is actually not clear. It doesn't have a sharp decay. So this is an example where probably there are no good clusters, okay? So here probably no good clusters are available, okay? You can also see that the observed and expected are very close, the two curves. Over here, you also see that unlike the previous case, we actually have a peak here, and then after that kind of like stabilize. This one is kind of like erratic, okay? So it suggests that there is actually no reasonable clusters. In fact, if you look at the result here, look at the result here. So this is the result of 1, right? Okay. So roughly, so though there is actually a 3 here, but actually this result is actually erratic, right? So roughly you would say that around here, right? So k equals to 1, 2, 3 are about the same, right? Statistically, they are not that different. So in this case, since they are not statistically different for k1, 2, and 3, so there's actually no reason to use anything other than 1, right? Okay, so they're not statistically different. So going by the principle of parsimony, you will just pick k equals to 1. Okay, which means there's actually no reason to separate into 3 clusters. Maybe you want to separate like that, but it's just not statistically any different from, let's say you have 1 cluster. Okay, so this kind, if you do data mining and you're desperate to find some kind of structure in your data, then this is kind of like a disappointing finding. Okay, so here is an example of applying the gap statistic to the classical iris data set, right? So everybody knows the iris data set, very famous. So here, basically, if I look at the two dimensions for sepal length and sepal width, right? So here's the distribution. So obviously, I'm not using the label information, right? So this one is just like I know it. So I want to see whether the unsupervised learning method can discover 3 clusters, right, without giving it the label, okay? Because that would be something that's very useful. So if you look at this data, you'll find that it actually picks up, yeah? So 3 is here. You can see that the gap statistic is actually increasing until 3, and after that it flattens, more or less, okay? So you see that the rest of these, their error bars are more or less overlapping, but 3 is actually the error bars are not overlapping with 2 and 1. Right? So suggesting that since all of these have overlapping error bars, so probably suggests that k equals to 3 is the best, okay? No reason to use 4, 5, 6, and so on, because 3 already is more or less the same as them, the gap statistic. Okay, so in this case, yes, you recover k equals to 3. Okay, which is good, because this is what you expect it to behave. Yeah. Okay, so so that's all I want to say about the k-means clustering, and especially the I think what is different from what I cover here is that this gap statistic thing usually is outside of the statistics circle, is actually not that well known. Most people will just use the standard k-means clustering algorithm, which is available in R. You can basically, I think it's one of the standard clustering packages, okay? But if you want to use good statistical results to determine k, then you have a tool here, right? Use the gap statistics. Okay, so I think it's just good time to pause until this part, okay, before we start the other part on ensemble methods. Are there any questions from you?
No here.
No.
I mean, like those of you who have worked for some time usually are very familiar with these two things, right? KNN and k-means. Is that the case?
Yeah, sometimes use it to do the binning instead of like discretize the column into quartile. Use k-means to discretize.
Does it work properly in your experience?
It works because we don't know what to choose to discretize. I don't know. Even try. Didn't really test.
Actually, you can take some idea from the way guide actually discretize its discretize the continuous variables, right? Last week I talked about how guide actually does that with
Yeah.
yeah, it uses it's something similar to your quantile methods, but he uses some kind of particular values, I think involving square root of 3 and something like that, which actually gives pretty robust results. So you might actually want to try that.
Okay.
Yeah. It's very surprising because that's the how guide actually works, and it actually works very well. So that method must be quite robust, I think.
Okay, then I'll try and see. Thanks.
So sometimes if you deal with problems that are not too complicated, maybe and only prediction is needed, then I guess your customer may be satisfied with KNN. If supervised case, or you want to do a very quick way to find out how many clusters are there, then the gap statistics or k-means will be very useful to you. Okay, okay, so it's 7:30, so let's take a break now and then we come back at 8 o'clock, all right? Hi everyone, can you hear me?
Yes.
Okay, so let's get started once more. All right, so now we are going into the section about ensemble methods, right? So, so maybe before this slide, I'll go to the notes. Okay, so I'm just going to go through this notes with you. So, okay, so basically ensemble methods, they are actually a powerful way to improve your classifier performance. If prediction is the ultimate goal, right? Because once the ensemble methods come in, usually you will lose model interpretability, right? In a while, you'll see why. But otherwise, if you just care about prediction, then they are a great way to maybe get further performance out of your model, right? Okay, so let me see. Let me just want to move things around a bit. Okay, can you see the text clearly?
Yes.
Okay, so basically, we have this is a classifier. This H, right, is a classifier. And basically, this classifier, it takes in the data, the observation, yeah. Okay, this is the ith observation, right? This is basically a vector, okay. So once you put it inside the classifier, then it will predict either -1 or 1, right? The binary classification, okay. So here we have the notation big H and small h. A big H is what we call a strong classifier or a strong hypothesis. So this a strong classifier usually will produce low error rates. Okay, it's like a strong warrior. Yeah. Okay, it can do a lot of stuff. On the other hand, you can use a weak classifier, right, denoted by the small h, or a weak warrior. So once you, anyhow, it's just a classifier. So if you give it some input, it will give you an output, right? But its error rate will be much higher, and also it will sort of give you error rates that are quite close to random guess. Okay, but it's slightly better. Okay, so it turns out that this ensemble methods has a very interesting finding, which is if you have a collection of a lot of these weak learners, yeah, let's say you have many of them, then on average, right, they will beat this strong classifier on average. Okay, so there are two ideas here. One, first we talk about bagging. Bagging is actually a short form for something called bootstrap aggregating. So basically, what does it mean? So this is actually bagging is very simple. So you have your data, which is like this. This is your data structure. These are your features, right? F1, F2, F3, until Fp. And here are your samples, 1, 2, 3, until n, right? So this matrix is n times p, okay? Then you apply bootstrapping, right? Okay, bootstrapping, so you will have, you bootstrap the rows, yeah? Bootstrap the rows. Okay, the bootstrap the rows are n times. Okay, if you n rows, then bootstrap n times. So basically, when you bootstrap, so you will create bootstrap, this will be a bootstrap sample. So basically, you might have, if you bootstrap, you might get something like 4, 6, 1, 1, something, right? So you just bootstrap the rows, okay? And then you have another bootstrap sample. Okay, and so on, all right? You can actually create, let's say, 1,000 such bootstrap samples, okay? Which are basically some kind of perturbation of your original data matrix, right? So with the rows, some of the rows can be duplicated, okay? And on average, a bootstrap sample misses out this number of times. This is because every sample, right? Every sample has a chance of 1 minus 1 over n of being not chosen, right? Every time, so you have, so every time you choose, right? Okay, so you want, each of them has a chance of not being chosen, right? Because every time each of them is 1 over n of being chosen. All right. So then there is a 1 minus 1 over n chance of being missed. Okay. So each of them has So each of them has a probability of 1 minus 1 over n of being missed. And you repeat that n times. So altogether, there are this is the probability that they will be missed, right? This amount, this is the probability that you will miss some of the observations, all right? These are the proportion of observations that will be missed. And this will converge to E minus 1, yeah, from basic calculus, right? Limit of this is equal to 1 over E, right? So on average, if you do bootstrapping, right, you will miss about 37 of your original values on the rows. Okay. Now, for each of these bootstrap samples, you will construct a weak classifier. That means here you can actually build a classifier. It can be a tree. Okay, it can be a tree. So this one build another tree. It can be an SVM or whatever. Okay. So basically, you build trees. Here I use an example, right? So each of these bootstrap samples, you use it as input to build a tree, for example. So then you will get, here in this case, you will get 1,000 trees. All right, so you get 1,000 trees. And this 1,000 trees, let's say you have a test sample. So this test sample will go to this 1,000 trees, right? Tree 1, tree 2, tree 1,000, okay? And each of these trees will give it a prediction. Okay. So each of these trees will give it a prediction. So for example, let's say tree Y gives prediction -1, -1, and this one, let's say, gives prediction +1, all right? So altogether, let's say there are 750 plus and 250 minus, right? So you go for the majority, okay? So you predict as plus, yeah? So you basically use large numbers of weak learners, and then you collectively use their strength, right, to make a decision. Okay, so so this is the idea of bagging, all right. Okay, let me see.
Doctor, using is stuck outside the meeting room right now. Yeah.
I think I just allow her to come in. I think she's in already. Okay, thanks.
Okay, thank you.
Okay, so this bagging is actually totally general, right? Just now I used the example of a tree, but it can be used for any classifier, because basically you have your data set, you build bootstrap the rows, and then over here you can apply any kind of classifier. You can have an SVM, for example. Okay, SVM 1000. So each of these SVM will make a prediction, plus, minus, right? And here we'll go by majority vote. Okay, so it doesn't really matter what classifier you use, right? Although in a lot of softwares, they will usually do bagging with the trees, because trees are good at capturing. It's actually known that for models that are able to capture complex data, such as a tree, the bagging will further improve it. Okay, so that's why most of the time you see that when bagging is deployed, right, they deploy it on things like the tree, right, rather than other classifiers. But if you really want to, you can actually, it's not hard to write the code, because you basically just need to, you can actually write your own code, because you basically just need to bootstrap the rows. and you create a function to create the bootstrap, and then you basically just iterate it 1,000 times. That's why you see this method is computer intensive, because basically you will have to repeat this, let's say 1,000 times. And over here, this part also has some kind of cost, right? Each of these model has a time cost. So you basically you are multiplying the cost of running one model by, let's say 1,000, by a factor of 1,000. So if it takes like 2 seconds to run one model, then basically over here you will have to take 2,000 seconds, right? More or less, if you are doing it sequentially, right? So after that, you go by majority vote, and that seems to be a very simple strategy that actually works. Okay, this is like using a committee of partial experts, right, to make a decision about some issue, compared to, let's say, you rely on a single kind of like very strong expert to make a decision. So it seems like in the long run, right, a committee of large numbers of partial experts, the decision arrived by them will actually beat the very strong learner. But this strong learner is an expert of a lot of things, but it's only one particular classifier, right? And this has some very interesting analogy with political systems. You can look at in some systems they are open, right, and some systems are closed. Okay, and it's been always discussed whether which system is better, right? Like an open system would be something like democracy, right? A closed system would be something like some military dictatorship, or maybe some kingdom or whatever. Okay, something where small, it's basically a system is closed, where this one is more like generally citizens can participate, right? All citizens can participate in offering opinions. This one is only a small group of people can participate. Essentially, maybe like in fact, if you have a kingdom, the king is the person who says everything, right? Here you have everyone can participate, right? So in fact, it is saying that even you have a group in the long run, it is saying that in this situation, you have in the long run, even if you have just some very weak, they are not very strong, they're not very wise people, but you take a group of them, each of them are maybe knowledgeable about different things, right? But none of them are knowledgeable about a lot of things. Here you have someone, this guy, who is like knowledgeable about many things. Okay, it is saying that in the long run, right, this system will do better than this system. Okay, even though intuitively we feel like this one is actually much simpler, right? Because the decision made is very you can trace it to one person, right? Here, this one, if at the end you want to find out who is responsible, then everyone is pointing finger to everyone else, so very hard to pinpoint, right? But this is in the long run, right? It is saying that in the long run, this system will produce some decisions that on average are better than decisions made by this single person. I think the idea is because over here you basically have a large variance. The problem is that this system has large variance. If this person is knowledgeable, but then depending on once you change the person, right? So you might actually get someone who is totally not knowledgeable, and then the variance, there will be a large number of variants. Whereas in this case, because you are relying on a committee to make a decision, do majority, so there's some kind of averaging effect that comes in. So in the long run, it seems like this is producing a result that's better than this one. Okay, well, at least this is what from machine learning, this is what is being shown. Of course, in real life there will be more complications, right? Yeah. So this is just something that I found interesting. So anyway, Okay, so here I have a small small space here. Then I said use linear classifier sketch in white space below. Okay, so basically if you do, you can actually use the example of linear regression. Right? So let's say linear regression, you have data like this. This is your, this is X, this is your Y, right? So you got rows 1, 2, 3 and everything, right? So basically you can do a bootstrap, okay? You can bootstrap your data. So you create a bootstrap of X, Y. Here you have a bootstrap of X, Y, okay, and so on, right? So each of these bootstrap samples, right, you can make a regression line, right? Because so you can make a regression line that's like this. Then this one, the regression line may look like this. The other one may be like this and so on, right? There will be a lot of regression lines, right? Okay. So now, let's say if you want to predict a value that is here. Okay. So let's say you have a test sample, you want to predict this value. So what happens is that you basically do an averaging, right? So at this value, this model, this weak learner is predicting this value. The other one is predicting here. This one is predicting here, and this one is predicting here. Okay. So all the different learners, right? They are making different predictions. Okay. And then what happens is you average them. Okay. You average them. Then that will be the prediction from the bagging of the linear prediction using bagging here. Okay. Now, in your undergrad, right, most of the time what you do is basically you have the whole data. You just basically estimate the line, and then basically you have this point, and then you just predict like this, isn't it? This is how you predict, right? Okay. Use the entire data, estimate the regression line, and then basically after that, for interpolation, right? That means you are not predicting outside of the range of the data. You just use this model that is obtained using all the data, and then you just predict like this. Bagging says if you create all these bootstrap samples, let's say you create enough of them, let's say 1,000, and then each of them do a regression line, and then you for this test sample you predict separately for the weak learners. When you average them, the prediction is actually more reliable than this prediction. Okay, so maybe next time you want to do some sophisticated regression prediction, you can actually deploy bagging in. You can basically deploy bagging and get some better predictions. All right. Okay, so then I go on to the next slide. Bagging. Okay, then I talk about random forest first. Okay, can you still see it? Random forest. Can you see my?
Yes. Yes.
Okay.
Yes.
Now, I think a lot of you have heard about this term, right? Random forest. Actually, random forest is very similar to bagging. For random forest, you have an additional step. Okay, it's actually an extension of bagging. Here are your features, right? You basically randomly pick after you bootstrap the rows, yeah. You basically randomly pick m of the p variables. Okay. Of course you can use, if you use m to be equal to p, then basically it's just bagging. Okay. right? Because if you just pick m equals to p, then basically you are using the whole set, right? So now what boost random forest actually does is that it tries to weaken the weak learner furthermore by only taking a random subset of your features. So basically they may pick like m less, usually m will be taken to be like square root of p, okay? In fact, in some extreme examples, they might actually take just one, right? So basically this is a parameter that you can actually set in your random forest program. So basically you randomly sample the column. So you end up with a sample whereby maybe here you have column 4, 5, 1, 6, let's say. And here these are some bootstrap rows. And this one may be 3, 2, 7, 4. Okay, so this is a sample without replacement, yeah, randomly picked. So this is without replacement, okay? Because it makes no point to replace the features because it's basically redundant, right? So don't need to you basically sample without replacement, right? Okay, only you sample replacement on the rows, yeah. So basically, once you do this, like let's say 1,000 times, you basically will have 1,000 such pseudo, what you call the pseudo data sets. Okay, they are actually not the real data set, but you're kind of like simulating some data sets that might actually occur in practice. Okay, so then each of these samples, you will make a tree. So each of these pseudo data sets, you make a tree. Okay, without pruning. Okay, so basically you do a complete tree without pruning because you already weakened the columns, right? So you will get, in this case, you will get 1,000 trees if you set this to be 1,000. And then each of these three again, as in bagging, right? If you give it a sample, you give it a test sample, so it will give you a prediction, right? Let's say binary case. So again, after that, you will do majority vote. Okay. All right. So basically, there's only an additional step here, which is you basically randomize the, you randomly pick the columns, and the m is generally taken to be square root of p. Random forest is one of those very useful if you want to squeeze something out of your classifier model, right? And you're using trees, and if prediction is something that you focus a lot on, then random forest is something that you should always do. Okay. Of course, if you're doing trees, right? It's okay, I think, to you can build two things. One is you can build the single classification tree. From that tree, you use that tree more for as an explanation, okay? Less for prediction, but you are saying that, okay, so the variables that got into the tree are the ones that are important in making decisions, all right? So you discuss the, you relate those features to the domain knowledge, all right? I think that is very still very valuable. But for actual prediction, you are saying that for actual prediction, you can actually improve on the quality of the prediction by using random forest. Okay, so you combine both things, right? And then I think this will be you're getting good two things in one go. The one thing is the interpretability, the other is the predictive performance. Okay. Okay, so So that actually it's just a very short part. Actually, random forest is not that complicated, right? The algorithm is fairly simple. Okay, so now we go into a more technical topic called boosting. Okay, but let's say before that, I just share with you the slides. Okay, so can you see the slides?
Yes.
Okay. So anyway, this one is going back to bagging, right? So for bagging, let's say in this case, you're using linear classifiers. So basically, these are the different classifiers, okay? So built from different bootstrap samples. So for example, this one from one bootstrap sample, this one for another, right? So basically, so all these are decision boundaries, right? So the final decision boundary that you have will be you group them together, right? So they will look like this. So you can see the, let me see. Okay. Decision rule is majority vote leading to a piecewise linear decision boundaries. Okay. So basically your decision boundary will be like this. Let me see. It should be like this. You basically combine all of them together. There are quite a lot of them together. So if you have a simple one like this, okay, so you take both of them. So that should be like, so let's say this one is, everything here is plus, everything here is minus, right? So you got two boundaries like this. So the part that is clear cut will be something like this. Like this. Okay. So this part will also be plus. So it's basically like you combine all the actually it may be easier to think of it like this. So let's say you have a sample point here. So like this line here will predict it to be blue. Let's say this one will say that it's blue. This one also say that it's blue. This one also says blue, right, below it. And these two, right, these two will say that it is actually red. So this one will say that because it's above this line, right? Above. So this one also says that it's red. So here you have 3 against 2, right? So then of course, then this point will be classified as blue. Okay. Maybe it's easier to think of it like that rather than to look at the decision boundary. Okay, so this is another example of bagging. You can actually bag the SVM, right? So this is the support vector machine. If you now over here, what is interesting is the following. So if you do the linear, SVM, right? If you do linear SVM, then every time you have this data, then it may be like something like this, something like this, something like this, and so on. Right? There will actually be many lines. Okay. What happens is that if you do enough of them, they basically will basically the part that they all agree on, they will more or less fall like this in this case. Okay, so in this case, when you do bagging on linear SVM, it will end up with kind of like a rotated rectangle like this, where so this will actually classify the circles properly, and then the plus also properly. Okay, so in fact, of course, here you could do a kernel SVM, right? If you do a kernel SVM, you will get something like this, right? And that is in a single model. And that would be what we call a strong learner, right? Okay, but what is interesting here is that if you only do linear kernel, you know linear kernels will not work well on this kind of problems, right? Because this is non-linear, okay? So linear kernels will fail, right? So the linear kernels are actually weak learners. And with bagging, okay, so bagging actually improves. You've got a whole bunch of weak learners. You can make them strong by bagging, right? So basically, in this case, when you do bagging, your decision boundary, you will get this inverted, this is rotated square, which is actually approximately the same as your kernel function if you had used some, let's say, polynomial function. So this is very interesting, right? So weak learners, right? So you see that individual classifiers or learners that are not doing well, right? They always make a lot of mistakes. If you collect enough of them and you do bagging, I mean, like if you use bagging to generate enough of them, they can actually do quite well. Okay, so this is the magic of bagging. Okay, so then over here, then okay, so these slides are to support boosting. So I'll go to the notes. Okay, so I'll go through the notes a little bit with you. Okay, so the okay, so here this is the difference here. So your bagging and random forest, right? They rely on a brute force approach to generate large numbers of weak learners. Okay, so they may not be, they are computationally intensive, and they are very simple to implement, but they are brute force methods, right? So they basically just keep on simulating, doing bootstrapping on the rows, and then doing random selection of the columns, and then produce lots of weak learners, and then use majority vote to give the prediction. This can be inefficient if you need to deploy this very often. Okay, so for example, if you want a real time, okay, you want to do a real time system, it may be too computationally costly, right? Keep doing bagging and random forest, so you consume a lot of computing resources, right? This motivated people to think about a more efficient way, okay, to use ensemble methods. And the idea is the following, right? You develop an algorithm that produces weak learners. So it's an iterative algorithm, right? A weak learner that at the T+1 iteration that improves on performance of the weak learner at the T iteration. Right? So basically, you have a sequence of weak learners. Okay, so H1, H2, H3, and so on. Okay, there's a sequence of weak learners where the error rates, if you have some error rates, the error rates are going down. Okay, so it's kind of like improving. So this guy is improving on the previous one, this one is improving on the previous one, and so on. Okay. And how do we do this? The trick is to give observations weights. All right, you basically put some kind of weights on the observations, so that the weak learners, they focus on observations that are misclassified by learners at earlier iterations. Okay, so that means they will try to adjust the learner, right, based on the samples that they made mistakes. And those that they are doing well, the samples are actually not so much concerned, right? So the idea is to give weights to these observations. And when you keep on doing this, right, your weak learners will gradually become very strong until you get a strong learner, right? It will converge to a strong learner when improvement in classification is no longer possible. So you go through a sequence like, instead of having a bunch of weak learners where you then take majority vote, you basically kind of like start with a weak learner, and then you kind of like let the weak learner grow in learn from the data, so that it becomes more and more powerful. Okay, so the one that I'm going to talk about is something called adder boost. Right, it's called adaptive boosting. So this is an algorithm by Freund and Shapiro. Okay. So the theory is actually simple enough to be discussed, right? That's why we cover adder boost. There are actually a lot of other boosting algorithms that are more modern, right? Something called XG boost, and there are many other more, okay, which are basically extreme gradient boosting and so on and so forth. Maybe you have come across that as well. They basically are kind of like using some idea that is similar, right? Which is you have a sequence of weak learners, you try to improve them to become a strong learner. They only differ in terms of their details, right? How this is actually done. Okay, so the idea is you start with weak learners that improve on the error rates. Okay, so let's look at the notation here. So okay, so you have the vectors, right? So you got n observed vectors. Okay, so this again, your y is your class label, so you have -1 and +1. So let the weak learner at the t iteration be this. Okay, so basically your ht is the weak learner at the t iteration. Okay, so then you feed it with data, right? So then when you multiply the weak learner, okay, remember the weak learner, right, will produce two output, either -1 or 1, right? Because you give it this weak learner is a classifier. So if you give it data, it will give you, if a binary case, it will give you -1 or 1. Okay, so when you multiply yi with the predictor, then what happens is that if your label is -1, right, and then the predictor is also -1, then -1 times -1 is 1 for correct classification, right? If the other one is 1, 1, so it's also 1. Okay, if your prediction and your class label are different, right, it will report as -1 because the labels have different sign. Okay, so that's why when you take the product here, it's equal to 1 for correct classification and -1 for misclassification. Okay, and then let wi superscript t be the weight of the ith observation at the tth iteration, right? So each observation actually has a weight, right? And the weight will keep getting adjusted, right? Throughout different iterations. And then the sum of the weights has to be equal to 1. All right. So the weight of all the observations will be summed to 1. And the error rate at the ith iteration is equal to, you add, over here it means you add the weights of the wrongly classified samples, right? You see the subscript here is I belong in wrong, yeah? So this one you only sum weights of wrongly classified samples, okay? Okay, so that will constitute your error rate. And you define an exponential loss function, right? So this is a loss function, okay? You can see here, yeah, exponential, there's nothing weird. So here, this is a parameter. So this one is a YIHT, right? Which is this part, correct classification and misclassification, right? So if you have correct classification, this will be 1. If you have misclassification, it will be -1, right? So basically, your loss function, okay, will be low if the classification is correct, because then you basically only have E of alpha minus alpha I. If it is a wrong classification, your loss function will be E of alpha I, right? So this is definitely lower than this one, okay? All right, and alpha T is what we call the confidence parameter. So it will measure the quality of the weak learner. So if the quality is high, alpha T is high, then the quality is high. Okay, so this alpha T is able to capture the quality of a weak learner, and then you can actually, it's actually an important quantity because it will allow us to do a kind of weighted approach to make decision later. Okay. So at the beginning, let all observations be equally weighted. So at the beginning, all the observations are 1/n, yeah? So same weight. Okay, and then for the iteration, the algorithm works like this. So to update, right, to update the weights, so this is the updating step of the weight of observation, the ith observation, right? So let's say your data has got observations 1, 2, 3, 4, 5, and so on, right? So this is the weight in step 1, weight in step 2, weight in step 3, and weight in step 4, right? So at the beginning, this is 1 over, let's say if you have 10, so this will be 1 over 10. And then after that, it will change, yeah? Okay, it will change depending on the performance of your weak learners, all right? So each of the observation will have a weight that is repeatedly being adjusted throughout the iterations. Okay, so the updating is given by the next update is given by the previous, the current weight multiplied by the loss function and divided by ZT. This ZT is the normalizing constant, right? Because you want to sum this to be equal to 1. So when you sum this, you get summation Wi of t exponential of this thing. Actually, this is a t, right? Xi equal to 1, right? Equals to, so divide by ZT equals to 1. So your ZT is of course equal to this thing, right? So this is the normalizing constant. Okay, that means this thing will make the sum go to 1. Okay, so here you see that this is the weighted loss function. Okay, at the t iteration. So the loss function, right, will also go through, will also change, right, at each iteration. So you can see the updating here. Okay, so let's look at some examples here. So at the beginning, you have 1 over n, right? So then the next update will use the previous one, then over here, right? Okay, so then you replace 1 over n, okay, from the previous one, right? Then you do it for step 3, then basically you use step 2. So this one comes in here and you make a replacement. You can see that now the denominator, you start to have n, z1, z2, right? So you keep on doing this, you will get due to t plus 1 by induction, you will get the denominator to be like this, okay? Which is a product of the normalizing constants, yeah? Okay, so and then take note of this thing. So this is our final, so this will be our final, this part here is our, okay, our strong learner, right? You can see that it is actually a weighted form of the weak learners, where the weight is actually the confidence parameter. Okay. Okay. So now, so what do we do with the weights? Okay. So how do we figure out how to estimate the weights, right? So the first thing we notice here is the following. So first thing we notice this, that we have to have this relationship. Yeah, because the reason is because over here, right? You have to you sum this will equal to 1, right? Okay, so so this thing here is a constant. You can move over here, so the product is equal to this part. Okay, so it's nothing complicated, just an algebra. Okay. So how do we decide the value of the weights, right? So how do we determine that? So this part here is actually this part, right? Okay, so one way is to minimize the loss function, okay? So to minimize the loss function, so this is your this whole thing, yeah, the loss function. To minimize the loss function means that you will minimize this product, right? Over here, you will use a greedy minimization. Because well, greedy minimization in this case is fast, right? Because to minimize the product, right? The joint, you minimize Z1, Z2. You minimize the individual Zs, all right? And you hope that by minimizing all the Zs separately, the product is also minimized, right? So this is the greedy approach, okay? Very simple. And this approach will basically guarantee some kind of local, you will reach some kind of local minimum, but it may not be the global minimum, right? But it has the advantage of being fast. Okay, so then basically what happens is that you basically rewrite your ZT. Okay, rewriting 2. So equation 2, where is that? Equation 2. So this is equation 2. Okay, so if you rewrite it, you can rewrite it in this form, yeah. Okay, equation 2 basically you sum from 1 to n, right? But 1 to n, there are those that are correctly classified and those that are wrongly classified, all right? So basically you can separate them out, okay? The part where they are correctly classified will have this form, and the part that is wrongly classified, all right, will have this form. The reason is very simple. Over here, when you have a correctly classified case, the yt times ht xi will be 1. So you end up with exponential minus alpha t. Otherwise, you end up with exponential alpha t for the wrong ones. So you can actually write this step here. And over here, by definition, yeah, the sum of the epsilon t is the error rate, right? So here, this is just the complement, right? So you have this. So your ZT now has a very nice expression. So after you have this ZT, right, you can, since you want to do minimization, right? So you basically do calculus, you take the derivative, right? Differentiate this with respect to alpha t. So you set it to 0, then you solve, you will get alpha t to be equals to 1/2 log of this thing, okay? And then you substitute this result into 3, okay? Substitute back here. So you will end up with ZT equals to twice of square root of the product of the error rate with its complement. Okay. And then after you have this result, you substitute into equation 1, which is here. Okay, put it to here, and you simplify. You will get to here. All right, just put it here. You will get so your alpha t and zt substitute into equation 1. You will end up with this form. And this is for the correct classification, all right, where you have, so the update becomes simple. The weight update for the ith observation is the present weight divided by 2 times the error rate, okay. For correct classification, let's check. Correct classification, so this will be correct, this will be 1, right? Okay. So my ZT is equal to 1 minus epsilon t alpha. E of minus alpha t plus epsilon t E of alpha t, right? And my alpha t is equal to 1/2 log of that, okay? Okay, so when I substitute this inside, I will get WIT Well, let's see. So this one is okay. So you basically over here you have to do. So over here when you have exponential minus alpha t, that will be exponential of minus 1/2 log of this, which is exponential log of this, okay, minus 1/2. So this will end up with et over 1 minus this square root, right? Okay. For this one is for correct classification. So let's work out the algebra carefully. T plus 1. So this part here, I will have square root of okay. And what is my zt? So my zt will be so e of this, I'll get this, right? Square root of this plus et. So over here, e of power of alpha t, that will be basically just square root of 1 minus epsilon t over epsilon t. So this will be square root epsilon t plus, okay. Okay, so basically there are two of them, right? Two. So then you replace, so you have over 2 square root of epsilon t, 1 minus epsilon t, okay? So basically then you cancel. And this, so you get WIT over 2 of 1 minus epsilon t. Okay, this one is for correct classification. Okay, so I think, yeah, so this one is, please change it. This one should be 1 minus epsilon t. Oh, I think it's like, I think I this one correct is here. This one is misclassification, right? So please change these two things, right? Okay. Now you can see this. So what is happening here in the denominator? So you can see that if the error rate is large, right? Okay. If the error rate is large, so the weight that is given, let me see, if the, okay. if your error rate is actually small, all right? If your error rate is small, you'll see that the ones that are misclassified, right? They will receive a higher weight. That means there will be more attention to these misclassifications. Basically, it is like the algorithm is focusing on the ones that you misclassify. Okay, if you are starting to have lower error rates, and the ones that are correctly classified, you'll find that over here is so 1 minus alpha, epsilon t will be large, right? So the correctly classified observations will actually be weighted down, right? So that means that the algorithm is not so much worried about them, right? It will focus on the improvement on the misclassification. Okay, so this is how the error rate actually affects your updating. Okay. So basically then you will iterate, right? So basically once you have this, you do it several rounds until you have the overall, so this will be when the error rate is exceeding certain, actually when the error rate is, okay, this is some stopping rule. When your error rate exceeds certain threshold, then you will stop. Right? So your final boosted ensemble model is given by the following. Take the sign of this weighted. So this is the weighted weak learners. Okay. So basically the weighted weak learners. So this is the confidence, right? So it tells you how much faith you want to put for a particular weak learner, and then you kind of like average them. Okay, so if this at the end you get minus 2.3, that means you will predict the sign will be minus 1, right? So you'll predict as minus 1. If you get something like 2.9, the sign is positive 1, right? This is a positive, so then you will predict it as a plus 1. Okay. So basically, this is how it actually makes decision using a weak learner. And in the example that we are going to cover, the weak learner here is a decision tree, but a very simple decision tree called a decision stump. So a decision stump is basically just a single node tree. Okay, it's a tree that has only one node and immediately splits to the terminal nodes, right? So in terms of the partition of the variable space, it's basically just a cut. The stump is basically just one cut on the horizontal, vertical, or on the horizontal. All right. Okay, this is a decision stump is a very weak learner, right? Because you only make cuts at one position. But as you can see, if we do boosting, you can actually create a strong learner from it. Okay, let's look at the example in the slides. Can you see the screen? What's happening?
Which screen are you asking of? It's like we can see the Wikipedia here.
No, not. Okay, not this screen. Stop share. Share the screen. Okay, this one.
Yes, the boosted line linear classifier.
Okay. Right. Okay. So this one is the Well, this one is basically just the previous. This is more about bagging. Okay, never mind. I'll just skip this slide. Okay, so go straight to this algorithm. Okay, the adder boost algorithm. If you want to see more details, you can actually check this PDF. Not sure whether it's still there. You can try. This is the PDF I think prepared by Freund and Shapiro themselves, right? So this example is taken from there. Okay, so basically, so let's look at this example. Let's suppose you have these 10 data points, right? 1, 2, 3, 4, 5, 5 plus and 5 minus. Okay. Okay, so here if you use a decision sum, right? The best, so you can think of how to put this decision sum, right? Put a horizontal line or vertical line through this two-dimensional space. And the best misclassification rate that you can ever do is 30%. Okay, no matter where you put, the best one, if you put here, let's say if you put here, then so here, let's say you go everything by negative, right? So this will be wrong. So then everything going up here, so the positive will be right, but this will be wrong, wrong, wrong. So you make 4 mistakes, okay? So the best position you can put your sum is here, all right? So other places you will make mistakes. Actually, there are other equivalent positioning, like another one is putting it here. So you will make 3 mistakes here, right? So that's also equivalent. Let's say suppose we start here, right? All right, so this is our stump. And okay. Right, so this is round 1, right? Okay, so how do we actually move through this? Oh, okay, so let's give our observations some kind of label. Okay, this is 1. This is 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So at the beginning, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at the beginning, we have so these are my observations, right? So at the beginning, my weight is everything is 0.1. Okay? 1 out of 10, right? So when I cut here, so let's say I cut here, right? So I make 3 mistakes, right? So my epsilon 1 is the sum of the wrong labels and their weights, right? This is 1. Sorry. This I, okay? This 1, right? So there are 3 of them, right? Make mistakes, 1, 2, 3, right? And 1, 2, 3 are making mistakes, okay? So these three, they sum to 0.3, all right? So this is okay. And then my alpha 1 is 1/2 log of, what's the formula there just now? Square root of, what was that? Can somebody just quickly refresh me? Okay, never mind. It's a 1 minus epsilon t over epsilon t, right? So this is 1/2 log of, so 0.3, so this is 0.7 over 0.3, okay? Can somebody calculate this? Check whether it's equal to 0.42?
Not really.
One eight three.
Huh?
183.
0.183.
183.
Oh, 184, yeah.
Log or log? Log log base 10.
No, that's log base e.
Log base e
Why all of you have this? Where did you get this notion that log is equal to log base 10?
Secondary
Calculator.
school.
When I write
Yeah.
log always means ln, you know. When it's a base 10, the 10 will be indicated. Otherwise, log and ln log is ln.
Yeah,
So I don't know
that is 0.
like maybe
Then it's 0.42.
the training you got from high school where you're being taught like that.
Yeah.
Yes.
No, log, if you don't put a 10, it means ln, you know. That's all this while has been like that. So I don't know, I noticed that now the students a lot, when I write log, right, they'll go and do log base 10, which I feel like, huh? So actually log, when I write log, it means base e, okay? Base 10 always,
Okay.
the 10 will come out. So, is it 0.42?
Yes.
Yes.
Yeah. Okay. It's E, okay. Okay. So we got this, right? Okay. So we got these two values, right? So then after that, so we will do the updating, right? Okay. We want to do the updating. So okay. So now which are the ones that were wrongly classified? 1, 2, 3, right? Okay. 1, 2, 3 were wrongly classified, right? Now you see the 1, 2, 3 here, they are wrongly classified. So you see they are larger, right? The font here. That's because they are receiving a higher weight now. Okay. So the weight is actually go back to the weight. Okay. The weight is I plus 1 is the previous one over 2 1 minus epsilon t. This one is for the wrong classification. Right? Okay. So if you have correct classification, it will be 2 epsilon t, right? This is the right classification. All right. So now, so let's try this. So WT will be the previous one. They are all 1/10, right? So this is 2. So you have well, let's just write 0.1 here. So epsilon here is 0.3, so that'll be 0.7. So this is 1/14. Okay. The other one is 0.1/2 times 0.3. So that's 1/6. Okay. So the one that are rightly classified will receive the weight of 1/6. The one that's wrongly classified will receive the weight of 1/14. Okay. So 1/14 will go to these cases. Someone's mic is on. Can you mute it?
Oh, okay.
Okay, thanks. Right, so these, okay, so 1, 2, 3, right? These are the ones that were misclassified. So they will now receive a higher weight, which is 1/6. Sorry, wait, let me see. This one is the, no, the wrong one is this one, okay. 1/14. Okay, the rest of them that are correct, okay, will receive this one. Wait, I think I swapped the two things. So this should be the correct. This one is the misclassification, right? So the misclassification should receive this weight, which is larger. This is the correct one, receives a smaller weight, right? This is 1/6. So all these are 1/14. Okay, so you update the weights like this. Okay, update the weights like this, and then okay, so over here you have, so the round 2 here, right? So the round 2, so you are making this cut. Okay. So over here, this cut, right? These 3 are making mistake. Okay. So these 3 are making mistake. So these 3 are what? Let me align this a bit. Okay, so these 3 are 7, 8, 6, 7, and 8, right? Okay, 6, 7, and 8. So that means you have to look at these 3. Six, 7, and 8. So these three guys are the ones that are wrong. So the error rate will be in E2, you'll be sum these three, so 3 out of 14, right? So 3 out of 14 is okay. 3 out of 14 is 0.21, right? And then you can plug in 0.21 to the formula for alpha, then you will get 0.65, okay? And then you will, after that, you will update, you will create an update for this column, okay? So you update this column, yeah, with the new weights. Okay, and finally you have one more sum over here. This is the third week learner. So you get this, right? So you look at this one. So now this alpha 3, the confidence is very high already. It's become 0.92. The previous one is 0.65 and the initial one is 0.42. So it's the confidence is improving. And then finally, your final hypothesis will be the sign of these three things, all right? So if you have a sample that is falling in this section, so this section, let me map here, right? Okay, so in this case, it will predict as, this is blue, right? 1, 1, 1, right? In all these three cases, you will predict as 1, 1, 1. So you will get 0.42 plus 0.65 plus 0.92. So this is definitely larger than 1. And the sign is, the sign will be positive, okay? So you can see that it will predict, so this one, if it falls here, it will predict as plus, okay? Now, how about if you have something that is falling here, okay, which is here and here. So in this case, if it falls here, you will have predict as the red minus 1 times 0.42, yeah? So, okay, it will be minus 0.42. Here, it will be plus 0.65, yeah? Because predicted as plus. Here also predicted as plus. So this one, you finish up, it is still positive. So this one, the sign is positive, right? So it makes sense that something over here is also predicted as blue. Now, what if you get something that is here? Okay, so here you have it here, here, and here. Okay, so let's see. So for this one, you will predict as minus 1, so minus 0.42. So here you have again minus, so minus 0.65. So this one is plus 0.92, okay? So this one you have actually minus 1.07 plus 0.92. So this is less than 0. So you will predict it as minus 1, the sign. So no wonder when you have here, you will predict as minus, right? So you can see that by combining these 3 weak learners, where you adjust, you give a confidence value to each of the weak learners, you can actually create a decision boundary that is actually that is actually this rectangular, okay, this rectangular region, right? And this actually does the classification very well. Okay, so end up the final classifier, right? The rule is this region, and this is predicting everything correctly. Okay, and this one you get it because of this function. Okay, so this is the magic of Adder Boost. So you can see that in complicated situations, right, it is able to be very flexible, all right, because it basically weights these are the weak learners, and then it judges it by a confidence parameter. You can see that usually the confidence parameter will keep on increasing because you know the weak learners are getting improved, right? So this one is better than the previous one. This one is better, right? So it is improving. Okay. All right. Okay. So yeah, that's a bit of theory about at the boost, right? Some calculations. So the main idea is just that I wanted to lead you to this part. Okay. The calculation is actually if you do the calculation with some patience, you can actually get the algebra right. Right. It's not something complicated. Okay. All right. So okay. So already 9:34. All right. Okay. So I think that's all I want to cover for the course. I think up to basically these are the things that I want to cover in the course. So next week we will have your presentation, right? And then after that, the test on week 15, I believe. You know the date already?
Yes.
It's week 15, right? Or 16?
I'm not so sure about which week is that, but I got the date, which is on 5th of February.
5th of February. That's okay. Maybe week 16, right? Okay, so I will do some kind of actually the test is actually open book, and it's just basically testing your application of the method set. So nothing very complicated, and some of the I'll say more about that next week, right?
Okay.
Generally, it's not theory heavy. It's just some common sense questions, and then conceptual questions, and then you are given some data sets and you work on that. Okay, so the theory part is just that I want you to have some idea about what's going on, but there's no point asking you the theory because you can always copy these things, right? So that's why I just go through it with you anyway, so that you have at least some idea that how these things actually work.
So actually, I would like to ask about the particular assignments, right? Because of like for our data set, I think it's having, I mean for the hepatitis C data set, we are having multiple classes there. So is it like we train our data on the two classes, which is the normal and hep C, and then later on only we observe the other points whether do we predict them correctly or we predict them wrongly?
So your hepatitis C data set is the majority class is normal, right?
Yes.
Then
and also
then there are like some other then the next largest class is what?
Should be hep C if I'm not mistaken.
Hepatitis C. Then
yep.
Yeah, I mean, like you can define the problem, right? I mean, like sometimes you have, I mean, it may be not much point to say a predict the other labels if there's not enough of them in the training, right?
Yep, it's like about, I think it should be about 7 if I'm not mistaken.
Yeah. So you can actually leave them.
Okay. And also, should I handle the unbalanced class ratio here, since it's already an imbalance problem?
Okay, I didn't actually cover that in this course.
So I can just leave it and apply, and then after that.
Well, yeah, I mean, like you can have a look at that, and yeah, because I didn't actually say much about. Actually, there something should be done about the class ratio, because when you have unbalanced case, then
it will be biased to the majority.
It's always biased to the majority class, you see. So yeah, the one way to do it would be the simplest one that well, there are some algorithms that will help you to pad.
Just put the ratio, is it?
You create pseudo samples based on your minority class. You will create pseudo samples out of that and pad your I mean, like artificially increase the number.
Oversampling, is it?
Yeah. So then you get a balance, and then you work on that. The other way is the simplest one is to kind of like undersample your majority class. So you undersample it. So you basically undersample it, and then you match it with, you use all your minority class, then you randomly undersample your majority class, then you make them balance, and of course there are multiple possibilities, instances where you can undersample them, right? So study the variation. So that means you might actually like need to
underfit the model, actually, right?
Actually, yeah, I need to do like maybe iterations of such undersampling, like I don't know, like 10 times. Maybe 10 is too few.
I
don't know, like how fast it would be to make one instance of calculation, because if it is easy to do, like for one undersampling, then you can basically just basically repeat this, right, for maybe like up to 100 times, and then you can average the result of the models to have a look.
Okay.
Yeah, I mean, like once you average the result, right, you should report the variance, to let people know the variability. Yeah, I think that would be a very simple way without any need for algorithms, any specialized algorithms to pad the minority class. And then at the same time, it would address the unbalance thing. But of course, the downside is that, well, you kind of like are not fully using the
data.
Yeah. But I think that is okay for just an academic assignment.
Okay. Yep. And also, if in that sense, right, I think we probably need to evaluate the model performance. That means we're gonna do our cross-validation, and so I mean, we're gonna do our cross-validation at the same time. We also do the trait test split, right?
Yeah. So and then that's a good question, because you do another cross-validation, then it will be kind of like the number of you need to do will be increasing a lot, right?
Yeah.
Okay. I think if you have this kind of situation, okay, yeah, of course, if you do cross-validation, then
yeah, that's why I'm asking whether, if like, let's say we should do a proper one, or it's okay to just like do it without the part of imbalance part. Then in the end, we try to evaluate whether how's the performance scoring using the train test and also cross-validation?
I think the models may be more sensitive to unbalancedness than lack of cross-validation.
Yes.
So yeah, maybe like you could just give up a bit on the cross-validation and just try to balance it. Of course, you could also do just for the sake of comparison, right?
Yep.
You could do one that is like using the really unbalanced case.
Yep.
And that means like you go ahead with the unbalancedness and then you do your cross-validation. That's like one model, right?
Yep.
And then you could compare it with the, you know, if you undersample and then you compare, like you see what the two results, how the two results look like.
Okay, understood. Yeah, then that's all for my question actually.
Okay.
Yep.
Yeah, okay. Okay, yeah, okay. So I think I will not take up much more of your time. So that's all for today. So thanks for listening, and I will be stopping the recording now, okay?